it from putting it out in the real world and letting people do unexpected stuff with it. That just shakes out more bugs. So the real difference between the feature series and the stable series is just time. All right, so MPI conformance. So there are multiple levels of the MPI standard. So there's been 3 major releases, MPI 1, MPI 2, and MPI 3. But there's been a couple of sub-releases in there, so MPI 2.1, 2.2, and so on. MPI 2.2, there was a bunch of things in there, honestly, that nobody cared about. And we just never bothered to implement them. Because even though we're a thriving community, we do have finite resources. And there's only so much time, and people don't care about working on the non-sexy stuff that no one is asking for. But we finally got around to that because we got some pressure from, frankly, the MPI forum saying, you really need to move up to MPI 2.2. So just a couple of weeks ago, we are finally MPI 2.2 compliant, got those last couple of check marks. MPI 3 was passed as a document last fall, and we actually have a lot of it done, but there's one major thing missing, RMA. These are our track tickets that are missing. Brian Barrett from Sandia National Lab is working on this kind of stuff. He hopes to be done by the end of the year, but that is really the last thing that we need to be a full MPI 3 compliant implementation. And if you care, we track it on our wiki. These are really the last 3 things that are left. If you don't know, in MPI 3, they completely revamped the one-sided interface, so the puts and gets and stuff like that, so that they actually make sense and are very well explained. Still insanely complicated, but very well explained now. All right, so some other things that came out in MPI 3. There are new, better Fortran bindings, and it's called the MPI FO8 module. And if you are a Fortran developer or any of the people that you work with and collaborate with are Fortran developers, please, God, have them use this. This is so much better than the old MPIF.H interface that was there. It actually does type checking. There are distinct types for handles. I won't bore you with all the features, but really it is better, and you should have people use that. It is nice and interoperable with the old stuff, so you can have nice legacy codes that, 99% of it use the old Fortran interface, and you write one new subroutine and use the new interface. So it was specifically designed to allow that kind of stuff. Matched probe is a neat little feature that there was actually a race condition with the old MPI probe. So now there's a way that you can probe and guarantee that if you're in a multi-threaded application, you're the thread that's going to get the answer for that probe rather than a different thread, have it steal it away from you and so on. Sparse and neighborhood collectives. So collectives are a big feature. I think we all know about bcast and scatter and gather and reduce and all those things. There are now new ones that say, oh, I only want to do a collective with the people who have my ghost cells, right? Say the people who are around me. And sparse collectives, so maybe not everybody in the communicator is going to participate. There are now weaker and more interesting definitions for what collective operations can do. And I'll put a caveat on this that Open MPI has these implemented, just like several MPI implementations, but they are not well tuned yet. So you'll get correctness, you won't get high performance out of these yet, but still it can be a very useful operation, particularly if you don't have to implement it yourself. There's a whole new tools interface called MPI-T, and I'm going to talk about that in a little bit, so I won't say anything about it now. Non-blocking communicator duplication. This was came from several user requests saying, for whatever reason, my application has chosen to make oodles and oodles of communicators. But sometimes it's really expensive to make a communicator, like when you do, because it's a blocking operation. And where does all the overlap of communication and computation go? It goes out the window. So now there's a non-blocking form that you can do test or wait on. So you can start duplicating it, go off, do some FFTs or whatever you're going to do for a while, and then do a test or wait, and you have your new communicator. Non-collective communicator creation. So this is a variant on that everybody might actually make the communicator at a different time. So it's non-collective, right? So these are related but different, and it's to address different use cases of I need to make a lot of communicators and I don't want to block for it. And then the H-index block data type, I put that just so that I could have a full slide. It's a really boring thing. It's just a new data type. All right, now on the Open MPI side of things, what have we done? So we've done all of that MPI 3 stuff. I didn't list the new one-sided RMA stuff because that's still being worked on. But let's talk about some of the stuff outside of the standard that we have put in Open MPI, because we've always tried to pride ourselves on providing a reasonable user experience with Open MPI. It's not just about getting the work done. It's about actually getting some help from your tools. And we're not perfect. There are certainly rough edges in Open MPI that we need to work on, and we always need to work on. But we try very hard to put in some cool, genuinely useful things for the user experience. So one of them is better support for more runtime systems. So a notable thing for that is PMI2, which comes in Slurm. And so that is actually for scalability. So they're doing runtime testing of launching 10,000 processes at a time and things like that. And I am not involved in that work, but I hear it's going very, very well. A new generalized processor affinity system. And I'm actually going to spend some slides on this later, so I'll go into detail about that in a few minutes. Better CUDA support. It's actually been very rewarding that NVIDIA themselves have been involved. They actually have a guy who comes to our weekly meetings, and he writes a lot of CUDA-specific code and making things all play well from an MPI perspective in terms of GPU to GPU communication. We did Java MPI bindings, which may seem kind of weird. Why on earth would anybody who cares about HPC use Java? It turns out that Java is not nearly as bad as it used to be. It's actually used a lot in enterprise systems these days. And it has been optimized a lot. It's actually very fast, nowhere near as fast as C or Fortran, of course. But it's actually fairly respectable these days. And there were more than a few requests for, hey, you know, we'd actually like a reasonable IPC mechanism for Java, because all the ones that are there are all kind of low performance and object based, and you know, take away even more performance for you. So maybe you could just give us Java bindings to something that is well known and understood and has been very mature and worked on for 10, 15 years. And so we did that. We actually got some Java guys, because I am not a Java expert, and said, you know, what are the natural way to do these things? So there was some very interesting work that was done there. And then we added support for some more transports. And like Bernard said, I'm going to talk about the Cisco one at the 4 o'clock talk. Mellanox has added some stuff for their MXM2, and they've done HCall, which is their offloaded collective support, which is actually pretty cool. And then Portals 4 support. Again, I'm not involved in Portals 4, but that comes a lot out of Sandia, Ron Brightwell and his group. All right, and this one was just added the other day from Nathan Helm at Los Alamos, and this is just the coolest thing ever. He just got this idea, and within a day and a half, he hacked this up, and it is just so cool. So it's for both Bash and ZSH. We get tab completion of all the MPI run command line options, and that includes, if you're an Open MPI person, our MCA parameters. MCA parameters are runtime tunable parameters. And we have something just shy of about 10 million of them. So remembering what they are, what their names are, and what they do can be really daunting. So now you can have tab completion. How awesome is that? So this is using the Cisco usNIC transport, because you know I got to be a little self-serving here. But if you just MPI run -MCA BTL usNIC and hit tab, it shows you everything that matches that, and it's exactly as you would expect, right? Because if you had just hit BTL tab, then you would see all of them. You know, it's exactly what you would expect, and it shows you the first bunch of the help string for each of those things. Really, that's just awesome. All right, so now let's go into a little deeper thing, into two relatively new things in Open MPI that you may or may not be familiar with. So one is this MPI-T interface that I mentioned. It's a new MPI-3 thing. And then the flexible process affinity system, because we think that process affinity is actually very important, and more than that, we don't know how users will want to or will need to use it, so we created this flexible one, and we want people to go play with it. All right, so the MPI-T interface, and if you know who that is, you're dating yourself. It was added in MPI-3, and it's called MPI-T because it starts, all the functions that are in there start with T, and it stands for tools. So the intent for this is that tool developers can add a bunch of stuff, but this is actually in your MPI application, so you can invoke these things too. And the goal of it is that you can get and set MPI implementation specific values, right? So you can actually say read performance values out of, how are the hardware counters doing right now? What is MPI doing behind the scenes when I do an MPI send? Can I read and set MCA parameters in Open MPI, things like that. So like I said, I kind of alluded to it in my examples there. There's two kinds, control variables and performance variables. And in Open MPI, control variables maps directly to our MCA parameters, and performance variables is a new thing altogether. All right. So we call them CVARs just because we're lazy instead of calling them control variables. So we have CVARs. And in Open MPI, you may or may not be familiar, we already have several different ways to get and set the control variables, right? So there's command line options, which we now have, did I mention the tab completion, environment variables and config files. And it's actually fairly flexible about how you can do this. So for us, control variables is now just another way to get to those MCA parameters. So you can basically programmatically list or set the MCA parameters within your application. Or more relevantly, a tool can do that inside of your application as well. So think of debuggers and other performance profilers, stuff like that. So here's an example. There are, it's, you know, C functions. There are no Fortran functions. We could not find a use case for Fortran. So the MPIT API is only in C. And if you want to use it in Fortran, do not tell me. I do not want to know. But the very first one you call is CVAR getNum, and you can actually call this before MPI init. So these ones, the MPIT interface is irrelevant to MPI init and MPI finalize. You can use it outside of that block. But the getNum just returns the number of control variables that there are. And then you say get info, and you can loop over all of them and say, oh, get me the info for 0, for 1 and 2, and so on. And it gives you a whole bunch of information about each one of those variables. So the string name, the verbosity level, I'll talk about that in a second, the type of the variable, because like MPI, everything is typed, so there's integers and doubles and so on. The type of the object, so you can actually have control variables that are specific to a communicator, for example, or specific to a specific data type, or so on. And then the writability scope, which I'll describe that in a minute too. So there's verbosity levels. And we made up this, it's kind of a 9-block thing. So it's 3 groups of 3. And we define 3 different types of intended audience for these things. So there's the end user, there's a performance tuner, and then there's an MPI developer themselves. And then within each of those 3 blocks, there's basic, detailed, and everything else. Right? So yes, it's 9, but it's just 3 by 3. Right? The intent here, and this was actually very heavily inspired from Open MPI because we have 10 bazillion MCA parameters. Most people don't care about the vast majority of those MCA parameters. They really only care about the ones that are needed to make their application be correct, like use this network interface or exclude that network interface or run this many processes and stuff like that. They don't care about the tuning things. A different level of, a different audience, a different level of user is the one who cares about, oh, let's set the queue lengths to this. Let's set this many buffers aside for that, and so on. So it made a nice division, and we went through and audited a lot of the MCA parameters. I'm not going to say we did them all, but we audited a lot of the MCA parameters in Open MPI and set them up according to this 9-block. Most of them ended up in the first 6, but we have a bunch that are basically for us that, you know, most users don't care about. You're really only going to care about it if you're developing Open MPI itself. All right, so here's how we interpreted it. A user is, like I said, correctness, really needed for correctness. And we really strive very hard to have as few of those as possible. So the example I cited a second ago was use this network interface, don't use that network interface, and so on. And this, if you're familiar with Open MPI, we have this command called info, which shows you all of our MCA parameters. And the goal was that by default, it just shows you the user level ones, just the stuff that you need for correctness. Because a common complaint that we got was, wow, when I run info, I just get overwhelmed with 6 billion MCA parameters. So now we hide all that from you. It's still there, but you don't have to get scared about it. And then tuner is someone who wants to tweak MPI performance itself. So they resource levels, buffer constraints, things like that. And then for Open MPI devs itself. And then the inner 3 levels, basic. It's kind of hard to say this in a non-condescending way. It's not meant that way at all, but it's for less advanced users and tuners, right? So for people who are just trying to run, they don't necessarily even know or care what the application is. They might be a technician. They might be a graduate student who was just told to go do this. They don't care. They just need to get it running, right? And then detailed is, you know, we had to give fairly loose definitions here because you have to apply this to every single parameter in the system. So we're like, well, it's something that is useful, obviously, or we wouldn't have it, but you rarely need to change it, right? So the default is almost always going to be enough. So, you know, they have to kick up to another level to be able to see that. And then 3 is just anything else that doesn't even fit in that category. Because when you go through all these MCA parameters, you're like, well, which 1 through 9, what do I put? And so we kind of created these rules of thumbs to help the Open MPI developers rank all the parameters. All right, and then there's a writability scope. So if you recall, the MPIT interface allows you to both read and write these values. And so the trick is, though, that with these values, it's up to the MPI implementation as to how you can write them and when you can write them, or if you can write them, because not all things are writable. So Open MPI, some of our MCA parameters are what we call info things. They just tell you something. It's not something that you can set, right? And so, for example, there are 2 read-only kinds. There's constant and read-only. So constant is that it's read-only and it'll never change. But read-only is read-only, but the MPI implementation may actually change the value over time. So you might have to check it again later. And then there's local and group semantics, right? So some things in an MPI implementation, sure, you can just change it in this one process and it doesn't matter. But other ones, you have to really set the same behavior on all processes, or your MPI is going to be inconsistent and unpredictable things will happen. So there's a way to enforce that, right? You can, the group setting says, it doesn't have to be the same value, but it has to be consistent for some definition of that MPI implementation. And then group equal means, no, it must be exactly the same among all MPI processes in the job. And if it's not, that's erroneous, and therefore random bad things can happen. And then the same, another gradation of that is all versus all equivalent, where you know, if one person or one process sets it, then everybody must set it. And if they must set it to the same value, and so on. So just different levels of whether you can write or not, and how. So again, just going in with a couple of examples here. I'm not going to go super deep, but these are the general flow of how you do it. So you allocate a handle, a control variable handle, and you give it the index that you got from the beginning, like, oh, I want to do, you know, index number 13, that particular control variable. And then you get a handle out, and you use that handle for the read and write call right there. Now, I'll give a disclaimer too here in Open MPI. There are very, very, very few things that are writable after MPI init, because basically during MPI init, we read all these MCA parameters and set up the state of the world. And back when we made the MCA parameter system, we really didn't envision changing the state of the world after MPI init. So if people find this interesting and say, you know, halfway through a run, I want to change something fundamental. You know, I want to change, like, oh, turn off the InfiniBand transport and use TCP. I mean, that'd be pretty stupid, but something on the level of that is kind of a world-changing event. If you want to do that, let us know. Right now, we're kind of assuming nobody does, that you might do this stuff before MPI init so you can do it programmatically, set some things, and then do MPI init and go on your merry way. But if there is something that you want to be able to do after init, send us some feedback on the mailing list. We'd like to know. All right, now, I was talking about the control variables. There are also performance variables. And this is new information that's available from Open MPI. So I'm going to talk about it in the second talk in what we've done for the Cisco devices. But we're basically exposing runtime statistics and performance variables. That was kind of redundant. But implementation details, right? So what's the hardware doing underneath? How many times have I sent that? You know, all kinds of things. We did first down at the network layer, but it could also be MPI layers things too, like how many communicators are being used right now, how many requests are being active right now, all these kinds of statistics that you like to see in profiling tools when you're looking and trying to find the bottlenecks in your application and whatnot. So it's a very similar interface to control variables, but they're all called PVARs instead of CVARs. Now, there aren't many available in Open MPI. As a matter of fact, the Cisco stuff is among the first group that's there. We export 24 of them so far, and we actually export them per network link, which is actually pretty cool. But there's going to be more over time. So we actually kind of did the Cisco one as an experiment so that we could set a precedent for the rest of the community about, hey, if you're going to expose stuff about your network, do it this way, kind of thing. And I'm going to talk more about those a little bit in the second talk. Okay. Let's talk about the process affinity system. By the way, I didn't say this before, but if anybody has a question, please feel free to interrupt me at any time. All right, yeah. Sure.
Most of the control areas, mostly you can set for MPI NIC.
Yes.
So most of these are already exposed to MPI 1. I'm just wondering what are the use cases for an example of some use cases.
That's a great question. So I'm going to repeat this for the online people who are not here. The question is, Open MPI has all these MCA parameters. What are the use cases for doing it programmatically rather than just on the MPI run command line or environment variables or config files? The use really is for tools, those who like to have graphical launchers, where they're going to intercept, they're going to launch your tool or launch your MPI application and then stop it. And they might stop it right when you enter MPI init. And then they can give you a nice GUI and say, oh, would you like to set parameters for TCP? Boom, I have this whole group of them. Click, 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 nice friendly GUI. And then they can actually invoke the MPIT calls in the context of all the individual processes. So that's one way right there. Another is automated regression testing or automated performance tuning. Like, oh, okay, I want to have a range of test these, parameters, these buffer sizes, and so on, these resource constraints for this particular transport. I'm just going to run in a loop and set them that way. Did that make sense? Yeah. So programmatically was the big theme that people wanted. Okay, process affinity. All right, so we've all heard this, but it's becoming really, really important because you can't even buy an UMA system anymore. Everything is NUMA today, right? Once Intel went NUMA, the whole world went NUMA, and that is pretty much just the universe that we live in today. So it's all about location, 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 right? You need to minimize the distance that your data has to travel. And it's not just on the network anymore, right? It matters inside the individual compute nodes. But it's really a multifaceted problem because you can think of locality as the same thing, regardless of whether you're inside a server or across a network. It's just different levels of locality, different levels of latency, but it's really the same problem. It's now just becoming a problem inside the box. And of course, we've had big machines that were NUMA for years and years, but now we're all NUMA, so it's really a problem for everybody. So this is a picture from HWLoc. If you don't know HWLoc, it's a sub-project of Open MPI that draws pretty pictures like this of the topology of your server. It does pretty print, it does PDFs, it does JPEGs, it does XML. It's a wonderful little Swiss Army knife of showing you the topology of your server. And let me orient you to this picture a little bit here. These are PCI devices. So this is a Cisco server that's a Sandy Bridge server. It's got 2 sockets, 8 cores, and so on. These are 4 motherboard 1 gig NICs. And then I have 2 PCI cards here with our fairly awesome VIC on it that they have 2 times 10 gig each. And you can see that these PCI devices are local to different NUMA nodes. That's actually a pretty important fact to know. And we'll get into why later. It shows all the L1 and L2 cache for all of these things. So you're like, wait a minute, L1, L2. Well, there's 2 kinds of L1. There's the instruction and the data cache. So there's the L1I and the L1D and the L2 cache above that. And it shows the sizes of each one. So the L1s are 32K and the L2 are 256K. Very, very helpful if you are trying to optimize your application for, say, dense matrix multiplication or whatever it is that's very cache sensitive. Really handy to be able to programmatically know, oh, there's a C interface to this, by the way, too. So very helpful to know, what your cache sizes actually are. Then there's a big honkin' shared 3 on this particular machine. In both sockets, it's just easier to highlight them individually. So this one has a 20 megabyte shared L3 cache across all the cores. All the dark gray stuff are the individual cores, and inside the little white boxes are the hyperthreads. So for this, just to make the picture a little more interesting, I turned hyperthreading on. So we have, 2 what we call PUs in there, programmable units, such that each core has 2 of those. That's why you get the idea. I'm stumbling over my words here. Yeah, so in most HPC applications, your hyperthreading is off, but it made the picture look a little bit cooler. All right, so with that as a backdrop, the big rationale of why we did this work was in the Open MPI developer community over the last 4 to 5 years, we've been arguing about process affinity. And everybody's got a different opinion of how we think users are going to use process affinity. And everybody had a well-defendable position about, no, I think users are going to do this. And so, no, they're not going to do that. That's crazy talk. They're going to do this. We finally came to the conclusion that we have no freaking clue what users are going to want to do and what you're going to need to do, nor can we predict what the hardware is going to do, right? We have an idea of what the hardware is today, and us vendors have a reasonable idea of where it's going to go in the next 2 to 3 years. Then beyond that, who the heck knows, right? We have a lot of guesses as we go towards exascale. Well, point of the matter is the software that we're making today is going to be used for a while. So let's just make it a flexible system and let the users figure out what they want to do and then give us feedback, because clearly we have been unable to do that ourselves. So you're going to look at this and go, wow, that is way more than I need. But that's the whole point. We want to give you more than you need so that you can figure it out what it is that you need and then tell us so that we can optimize those patterns for you. All right, so there are actually kind of 2 complementary systems inside Open MPI. There's the really easy one to use and the really flexible one to use, right? So the easy one is, oh, I want to bind every process to a core, or I want to bind every process to a processor socket, and so on. And then the second one is, how do I want to lay them out? Do I want to lay it out by server or by, we call it by slot, which is usually a core, and so on. So there's 2 kinds of things there. You know, what do I want to bind it to and how do I want to lay them out? And then the flexible one is something that we call LLAMA, because you need a 4-letter acronym, otherwise it's not real. It's the locality aware mapping algorithm. We've actually published some papers on this, and I presented this in Madrid at the Euro MPI conference a couple months ago. But LLAMA, the whole point of LLAMA is to support a wide range of regular expressions of patterns, both patterns in binding and patterns in laying out of things. And we drew on, you know, I don't think we always give enough credit to the people who have come before us. So we really are standing on the shoulders of giants. There's a mountain of prior work on this, and we in particular drew a lot on the BlueGene system, the way that they do process affinity there. We just kind of extended it and added some cool things on top of it. All right, so in Open MPI, we break down launching applications into 3 steps, right? So there's mapping, ordering, and binding. And I just wanted to show you those 3 terms, and now I'm going to talk about what each of those are. So mapping is a layout of processes to resources, and it looks like this. Let's say I have a bazillion processes that I want to launch, and I have a bazillion servers to launch them on. I need to create a map of what process is going to land where, right? And in that, we kind of, it's processes to processors is really what the map is generated of. Memory is important too, but that's a secondary effect. It's mostly to processors. And we have this natural air gapping boundary of servers, right, in commodity clusters. So the basic technique of what we do is when you type MPI run, it goes and launches these little helper daemons on all the servers that you identify, and it gathers the HWLOC topology. So remember the picture I showed of a server before. It gathers all of those from all the nodes and builds a map of what's available. And then it says, oh, okay, if I'm going to map by core, what process am I going to put on each core, and so on. And it creates that map that way, basically. So it's a plan, so to speak. All right. And in this, OpenMPI is fundamentally built on plugins. So we have a mapping agent plugin, right? So the act of planning involves several different things. So no matter what plugin mapping agent you use, whether you use Llama or whether you use one of the simple ones or so on, it does several things, right? So it specifies which process is going to land on each server and identify any hardware source if it's going to be oversubscribed. Oversubscribed is a really hard thing to know. This is one of the arguments that we had over the years. What is the exact definition of oversubscription? Turns out people have very different ones. Some people don't care about hyperthreading. Some people do care about hyperthreading. Some people say, well, I only want one process per core or per socket. So if you put more than one than that, then that's oversubscription. So we needed to provide a flexible way of having a definition of what oversubscription is. So we, and I'll get to that in a second, but the background to get there is that processes in our mapping agent are always defined as mapping to the lowest unit possible, which is a processing unit. It's HWLOC terminology for as low as a hardware thread or a hyperthread, right? So usually in HPC, this is a processor core, but it can be as low as a hyperthread. I'm sorry, I say hyperthread, I really mean hardware thread because hyperthread is Intel's word for that, but it's a more general term. So the usual definition, what people mean is that when a single processor unit, hardware thread or core or whatever that is assigned to more than one process. Not always, but that is what we usually mean in the HPC world, right? But complicating that definition is that some processes are multi-threaded, so I might need more than one PU. And so therefore, it just muddies all the definitions. What exactly are you going to do? So something that took us a long time to figure out was how can you quickly and succinctly and correctly specify what you mean by oversubscription? And I guess I'm not going to answer that in this slide. I'll come up to that in a second. Next, so if you recall, I said we do mapping and then binding and then ordering. I'm sorry, mapping, ordering, and then binding. So let's talk about ordering here. That was mapping. We're assigning MPI COM world ranks, and I couldn't write MPI COM world because it went off the slides here. So MCW ranks to map processes. And common misconception, most people, when they're talking about MPI, they say, oh, what rank is on this node? Every MPI process actually has multiple ranks, right? So the correct term is actually MPI process. So these are all individual MPI processes. You can identify them by their rank relative to a specific communicator. So I'm talking about the MPI COM world communicator, which is what most people usually mean. But when you say, rank 3 in MPI COM world, that orange circle is the process that I'm talking about. So there are two common orderings that people do. One is what we call by slot, right? Where you go just boop, 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 and, kind of go by core, sequentially through a server, right? But another one is by node, where you see all the numbers change there. So it went 0, 1, 2, 3, 4, and so on, right? And it just lays them out differently. Depends on your application, which is right for you. Many people prefer this ordering because you have dense, close mapping of COM world ranks, and you have nearest neighbor communication in your application, and you want them to use shared memory instead of a network and things like that. But there are reasons to do this kind of mapping as well for certain applications. They don't necessarily care about the locality, or they actually want to exploit some other type of network property. All right. Each process has to get a unique, this is kind of one of the fundamental tenets of MPI, that you get a unique rank in COM world ranking, starting with 0, going to n-1. We call this natural and sequential, right? So whether you're going to be mapped, the order in which processes are mapped is the same as their ordering, right? Or sequential is, it doesn't matter how you mapped it, just go sequentially across the node. I'll show a picture of this in a minute here. Now, the third step is binding. Now, binding is enforcing the plan. Binding hasn't become very important until recently, but usually MPI run would just launch the processes, and you kind of rely on the operating system to not move them around and not trash your caches and things like that. But when you do binding, you're actually going to enforce the layout. So you could say, COM world process or COM world rank 0 is going to actually be bound to that processor core and all those L1 caches and so on, right? And there's a lot of different options for how and where you want to bind things. Right, so a lot of different options with that. The first one is, I don't care, just do an MPI run, just launch them, let the OS take care of it. That's good enough for me, right? A second one is this limited set of restrictions, right? So these are our processor sets and so on, where the operating system or the resource scheduler such as Slurm might say, oh, well, I'm actually launching 2 different MPI processes or 2 different MPI jobs on the same server. And so I'll give one of them half the cores, and I will give the other one the other half of the cores. And so you can play anywhere within your sets, but you can't migrate between the sets. And then the other is a specific set of restrictions where, nope, this process must go in this core, this process must go in this core, and so on and so on. So the term that we came up with to describe this is called binding width. And we say that that is the number of PUs that each process is bound to. It's just think of, oh, how wide am I allowed to play? How big is my sandbox? All right. So we have what we call 4 different levels of this. For all of this binding, ordering, and mapping, we kind of gave 4 levels of classification to this. So the first level is you don't specify anything. You just say MPI run my process and let the runtime system figure it out. And that is what 80% at least of users do. You might specify a number of processes, but you've left it up to Slurm or Torque or whatever your resource manager is to figure out the rest. The second one is what we call simple common patterns. So, oh, I want to bind to core and I want to map by server, right, or by slot. You know, very simple, easy things that probably cover the vast majority of the rest of that 20%. And then the third one is this Llama process. And I'm going to get into the Llama layout here in the next couple of slides, but I want to do something more complicated than just binding to core or, you know, or mapping by slot or something like that. And then, of course, there's always a couple of users who want to do something just completely different. They want to do different things on different nodes and so on. So some kind of irregular pattern. We do have support for that. I'm not really going to talk about that today. All right, so the first one, like I said, you may or may not even specify an NP. It's just you're going to trust the OS and the resource scheduler to put things where they go, right? And Open MPI for a long time has supported you know, various resource schedulers like Slurm and Torque and so on, and we will read from them. If you allocate, you know, 30 machines, we will find out from the scheduler where they are and how many processes you should use and all these kinds of things. Our default is to map in the, you know, by core style, so we will launch 1 process per core. We don't actually bind. We keep arguing about this, but for backwards compatibility reasons, we don't bind by default, which actually makes me a little sad, but hopefully we'll change that sometime soon. Now in level 2, there's basically 2 main MPI run command line options, right? So there's map by X and bind to Y, right? And there are various different values of X and Y. But you can pretty much infer from that what that means, right? So map by socket or map by core or map by L1 cache, right? The server that I showed before had unique L1 caches for every core, but some machines aren't that way, right? So some machine in L1 cache is actually shared across multiple cores, or probably more interestingly, an L2 cache shared across multiple cores. Maybe you don't care about cores, maybe you care more about cache size. So you might want to map by cache size instead of by core, for example. Now, everything that we do here in this level 2, map by X and bind to Y, has a direct one-to-one correspondence to the level 3 stuff, which was very important to us so that we only have really one system and we're exposing multiple layers to get to it, multiple degrees of flexibility. All right, and level 3 is this regular patterns, right? So I talked about Llama in the beginning. I haven't really talked about it since because, you know, everything I talked about so far is how Open MPI launches, binds, maps, orders, and things like that. Haven't really talked about, all right, now how do we give you flexibility into that process? Well, let's dive into that now. And again, this is something that we really think is going to be for power users, and not a whole lot of people are going to use it. Yeah, Eric.
It looks like most of the stuff is on the initialization. Can you change this at one time so if you're not, well, you know, this part of my algorithm,
Great question. So I'm going to repeat again for the online people. The question is, it looks like everything I've talked about so far is done at MPI startup time, so MPI init and earlier and so on. And the answer is yes, that is true. And then the further question is, can we change that afterwards? So if the application says, oh, my application, I'm going to spawn a bunch of threads, and therefore I want different affinity, or I want each thread bound to a different place, or something like that. We don't offer that as a feature of Open MPI, so we just do all the startup stuff. But then you can change your own affinity after that. So we actually link in the HWLoc library, or you can link it in yourself and make HWLoc calls or whatever your favorite affinity calls are. You should really use HWLoc because it's a nightmare if you don't, to change it. But we don't really have any features for changing after the fact. Okay, so there are, to get into Llama here, there are 4 relevant MCA parameters. And they follow our same prefix rule that we do in all the other parameters. They start with R maps. It might look kind of hard from far away, but it's actually R maps. And then Llama, and then map, bind, order, and MIPR. And map, bind, and order is pretty much exactly what I just talked about. You can infer that these are going to affect those steps that I talked about a few minutes ago. And the last one is the maximum allowable of processes per resource, MPPR. And that's the definition of oversubscription that I was talking about before. Yes? I'm sorry, say again?
What's the resource in this case that you use?
I will get to that in a second. Let me defer your question. The question is the order, I'm sorry, is the unit that we're talking about PUs? The general answer is yes, but I will get into some detail here in a sec. All right, so let's talk about the first one, the mapping one. So this takes an argument of what process layout do you want, and you give it a series of 9 tokens, which allows 9 combinatorial different orderings. The orderings of these tokens says how you want things laid out. So you're basically, think of it as 9 dimensions, and you specify which dimension to traverse. And so you're specifying the order of dimensions of traversal. So the 9 tokens that we have are node, which is really a server node. Unfortunately, node is kind of an overloaded word, NUMA node or server node. But we mean server node here is a little n. B for a motherboard. That one's kind of not all that useful, but when we were doing it, Oracle was one of the people helping us, and they had a multiple motherboard server. And so that was actually a cool dimension to traverse, but as far as I know, no vendor has any multiple motherboard servers anymore, but the token is still there. Processor socket, processor core, hardware thread, and then L1, L2, 3 cache, and then a NUMA locality. All right, so depending on what your particular hardware layout is, these dimensions may or may not be useful to you and so on, but they are all there. So basically, you're giving, like I said, the order of dimensions of traversal. And the innermost iteration is specified first. So the shortest distance that you're going to go first is the leftmost token. I'll show an example of this as well. Great question. Let me show you the example before I show you what the default is. All right, so here's an example system. This is kind of a dumbed down PowerPointified version of an HWLoc picture of a system so that I could put numbers and things in here. So we have 2 NUMA localities. Each one has 4 processor sockets. Each one has 2 cores and 2 hyperthreads. Okay. So I wrote that up. 2 servers, 2 nodes, 4 sockets, 2 cores, 2 PUs. Right. And let's look at this one. So if we map by SCBNH, right? So that's socket, core, motherboard, server node, and hardware thread. Right. So first, what that really translates to is first by socket, then by core. Okay, let's look at that. So you can see these are COM world ranks, these numbers in white. So 0 is on the first core on the first socket, then 1 is on the first core on the next socket, 2 is on the first core on the next socket, 3 is on the next core, or the first core on the next socket. Okay, now we have run out of sockets, right? Because this is a whole different server, right? I think I said that wrong in the beginning, that there were 2 NUMA localities. That was wrong. It's 1 server, second server, right? So now we go back we go into the second dimension, and we now traverse by core, right? But so now we're in that second dimension, we traverse the first dimension again. So we go, right, the second core in the first socket, the second core in the second socket, second core, and so on. Okay, now we've run out of both sockets again, and we've run out of cores again. So we do motherboards, but there's only 1 motherboard, so therefore we've run out of those again. Now we do server nodes, which means we go down here, right? And we repeat that pattern all over again, right? And I think I have blah, blah, blah. I skip all that. And once we hit 15, we've run out of that. Then notice the last token is hardware thread, right? So now we repeat that pattern with the second hyperthread in all the cores and all the sockets, blah, 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 okay? So again, kind of complicated, but super flexible, lets you do whatever the heck you want to do. All right. Now, binding width is, I mentioned what binding width is before. This is how you specify it. You specify it as a number and a token. So if I want to have my processes bound to 3 cores, I say 3C. That's kind of a weird binding width, but it's a great example. So that process is going to be bound to those 3 cores, including all the caches too, but I just wanted to show the 3 cores there. All right. You could also say 2S, right, for 2 sockets, which would bind my process to all the cores on these 2 sockets. All right. So any of the same tokens I listed before with an integer before it. Yes, sir. Great question. Can I defer your question for a couple slides? The question for the remote people is, this is so complicated, how do I verify I got what I want? I will show you. Yes, there is answer, a little teaser. All right. Another bind, and this one is kind of weird. We had a token clash, basically. If you want to bind to everything in an L2, right? I said verbally before, maybe you want to iterate by something other than a core or a socket. Well, you might want to iterate over an L2 locality. It's kind of weird because the token is a 2. And so it looks like 12, but it's really, I want, one L2 locality. Right? So I am bound to all the cores, or actually more specifically, all the processor units that are in that L2 locality. Right? So Open MPI is smart enough to say, oh, it's not just the cores that are in whatever you said, it's all the PUs. So if you have hyper-threading on, it will do the right thing. All right, and then here, one NUMA locality is just everything that's in there. All right, so then ordering, I glossed over this before. I said we have natural and sequential. Here's what it looks like. It's a lot easier than it sounds. So natural order for map by node is however they were laid out when we did the mapping, right? Whether it was by node or by slot. Sequential ordering is always the same. It's always sequential within a server. All right, so if you did map by core, then natural would be the same as sequential. Right? Now, we can actually be much more flexible than this in the ordering, but really we couldn't think of any other useful patterns. We said this is already complicated enough. Let's not give a lot of flexibility in the ordering step of this. But if users want that, please let us know. If you need some kind of wacky ordering of COM world ranks, let us know. But these are the only two, literally, that people have ever asked us for. So we didn't go hog wild on that. Okay, and then MIPR. MIPR is, like I said, the definition of oversubscription. So maximum number of allowable processes per resource. All right, so basically what this is I am specifying how many processes are allowed to be in this sandbox at most. And if I exceed that number, you are oversubscribed. Okay, let me just give you an example of this. 1:C means at most 1 process per core. And for most of HPC, that is a perfectly fine definition, right? But here's another one. At most 1 process per core and at most 2 processes per socket. Right? You might want to do that for memory constraints, for example. Like I have more processors than I need, but I want to spread you across the NUMA locality. Let me show you what that looks like. All right, so 1C, at most 1 process per core, no surprise there. But 1C, 2S means I'm only going to use those 2 cores because I'm not going to go more than 2 processes for the whole socket. Right? Again, you might want to take advantage of however much memory is in this NUMA locality, and you've got 2 processes that are going to malloc all of that up. It depends on your application. So this is more flexible than you would think just by looking at it. And it kind of takes a while to wrap your head around it. It took us 2-3 years to come up with this. We hope it's useful to you. Please let us know. All right. So now I said that there was a mapping of level 2 to level 3. If you remember, level 2 is the simple ones that we expect most people will use. And level 3 is this super flexible system, right? So if you look at level 2, there's map by, and all nice, easy words to use. L1, socket, board, and things. And then bind to, core, socket, and so on. Nice, easy words to read. But they all have exact equivalents with those series of tokens and the definition of oversubscription and so on, right? So if you bust out those individual letters, that's exactly what, map by socket would be, turns into SBNCH. So you asked earlier, what's the default? Our default is map by core, bind to none, right? So that actually turns into this with a MIPR of 1 to core, so we will never launch more than 1 per core, and we actually don't do any binding. Well, we bind to the whole server, which is effectively the same thing as not binding, right? Now, the big question is, so if I give you a definition of MIPR, that affects the mapping, right? Because if you recall this picture, right, I will not map basically on the rest of these cores, right? And basically, MPI run will error out if you ask for too many processes, right? So if what you have specified will result in an oversubscription, MPI run will say, hold on, you just told me to oversubscribe, error. And therefore, it lets you know. So that's the first way that we let you know that you're getting the binding and the mapping and the ordering that you want. Sorry, I guessed what slide was next incorrectly. So I'll get into the other part in a second here. But let me give you another example here. So let's say we're running 24 processes. And I picked 24 not because it's useful, but because it makes a nice uneven example down here. See, less processes here than there. It's just good for example. Now I give a MIPR of 2 per core, right? Which means I'm going to be using my hyperthreads, which is a pretty stupid idea, but it's good for an example. And I'm basically mapping by socket, right? Socket, core, board, node, hyperthread, hardware thread, right? And this is the example we went through before. Well, what if we did something slightly different? What if we said node, board, socket, core, hardware thread? The numbers change, where things end up. And I'm not going to go through this in detail here. The slides will be available later, but you can look through and see where things end up. So remember, over here, it was heavy at the top, right? And there were empty hyperthreads down here. Whereas in this case, it's much more universally distributed that on the second core, the second hyperthread is empty. I keep saying hyperthread. I really should say hardware thread. Sorry, Cisco is an Intel shop, so that's what I think. All right, so it's very flexible. You got to work your head around it, but it's very, very flexible. All right, so now finally back to your question, sir. How can you tell what you get? Well, we have a pretty print representation to show you what Open MPI is going to do for each process. Visual feedback is really helpful, particularly when you're trying to wrap your head around this representation here. So the way you specify these things is you have to give a bunch of MCA parameters. And again, this is why it's oriented towards power users, right? So you have to say, use the llama rmaps component. Here's the bind. I did a 1C, right? And then I did a NDSCH, and then a MIPR of 1 to C. And then this magic guy, report bindings. And you can't possibly read this, so let me blow this up a little bit for you. On the right-hand side, it'll say, hey, COM world rank 0 is bound to socket 0, core 0, hardware thread 0 and 1. All right, so we give you, I'm sorry, that's the left-hand side over there. And then we give you a pretty print representation of that. Like, oh, every dot is a hardware thread. The slashes are the cores, and the brackets are the NUMA localities. Right? So you can see that this process was bound to the first 2 hyperthreads over there. This guy was bound to the next 2 hyperthreads. This guy was bound to the first 2 hyperthreads of the next NUMA node, and so on. All right, and we list over here. No, I didn't show it in this example. The server name is listed in there as well, so you can tell. Okay, so incredibly helpful for determining that, holy cow, that is not what I expected at all. Eric. Wow. Great question. So let me repeat that. Eric, Mr. Checkpoint Restart guy, is tagging me on something that we didn't think of. He said, can we use these flags for UMPI restart? The answer is no. We should go fix that. Yeah, I know it's broken. Let me ask me about Checkpoint Restart in the QA session. I actually have something to say. But yes, that's a very good point. Could you do me a huge favor and send me an email reminding me that we don't have that? Thank you. In the QA session, which we're almost there. We're almost there. All right, so this llama stuff, the flexible stuff, is all available in 1.7.2. The MPIT stuff is available in 1.7.3. There's more stuff like these performance variables and whatnot are coming in 1.7.4. I'm sorry, 1.7.3, which is due by the end of this year. And so on. So this is really open questions for you, right? We're back in our little caves developing MPI, but we don't necessarily know what you all are doing in the real world. And so we need to know. So let us know, is this useful? And we expect that only some of you are going to use this, that's fine. But if you find yourself doing these same patterns and there's a whole class of applications that do these same patterns and you're like, I don't want to keep typing SBNCH because the biologists have no idea what that means. Cool, we can put in a shortcut for that. But let us know what are the important ones because we really don't know. Okay, so Paul, go ahead.
So first of all, I've been looking at your blog, not your email.
Sure you have. Sure you have.
Is there things right up there?
Yeah.
Because I wanted to find the answer instead of looking at the question.
Mm-hmm.
When you, if I recall correctly, when you showed the HWO visualization of your node, you showed two NICs.
I did.
So where's map to NIC? Where is MPPR for NIC?
So actually, that's a really great. We have, so Mellanox put in, all right, let me repeat the question. Paul pointed out that in the HWLoc picture that I because of the live stream, I can't just zip back to that slide. In the HWLoc picture that I showed, I had two NICs. So why is it NIC one of the tokens that we can map or bind to, basically? And that's a really good question. We did this, well, that's a really good question. I don't have a good answer for that. But I will say this, Mellanox put something in that I'm not clear on all the details, but it is something about nearest neighbor to NICs. There's a mapping to NICs, but it's not in exactly this way. I don't have a good answer for that. I should probably do a blog entry on it, and I'll take a note to do that right now, because I am flummoxed and do not have a good answer, which is embarrassing. Yeah, that would be great. Send me an email. They did something along those lines. I'm not clear on the details. But you're right, it really should be another token in there, because everybody should buy more NICs. That's what I say, and therefore more network ports. And
I can kind of figure out how to do it if I know that there is one I/O bus per Newman node. Yeah. I could use the Newman node, but if it doesn't work out that way,
yeah,
then if I've got two new nodes are close to that bus and two are close to the other bus, I don't have any way that I've helped from HWO and their binding mechanisms to try to allocate branch processes, whichever you want to say,
right,
to the specific nodes.
Now that's a really good point, and that's something. Send me an email, because we should. That's very good feedback. Any other questions, comments about this, about Open MPI, about MPI, anything? That is, so, all right, a couple things you said there. So the question is, what about the network hardware? Can we expose some of the information that's coming up from that? Packet sizes, latencies, things like that. Let me break that down into a couple things. From the hardware itself, yes, we can expose these kinds of things. Like I said, the performance variables, very early days. That was literally, all the infrastructure for that was just put in, say, 2 months ago or so. It was a fantastic work by Nathan Helm at Los Alamos, same guy who did the tab completion. So not many of the network transport BTLs and MTLs and so on have taken advantage of that yet. And like I said, Cisco was one of the first ones that we did, because we're like, all right, let's kick the tires and see what we can expose. And we actually ran into some fairly interesting issues. So we expose a bunch of things from the network layer up, but none of the other BTLs do that yet. So we expose things like the MTU, your packet size, well, your max packet sizes and things like that, the number of packets that have gone out. I'm just about to add some more from the hardware counters of the VIX itself. And this gets a little complicated too, because I can report stuff from the VIC, but that's global across all the MPI processes on that server. And it might not be global, it might not be equally global. For something I'm going to talk about in the 4 o'clock one. So in a NUMO world, in the usNIC one, we use the VICs unequally, depending on where you are. And so it gets complicated. We can report that stuff, but how would you interpret it? I don't know yet. We're going to expose it and see what people do with it. But anyway, point being, yes, we can expose all of that. I would encourage you to send something to the Open MPI developer community and or your favorite vendor saying, please do expose it. Did that answer the question? Yeah. Okay. Yeah. Correct. Correct. Because as of today, in MPI 3, the only thing that MPI cares about is a process. There is huge debate in the MPI forum about how do we play nicer with threads. Like, do we want to give ranks to threads? Do we want to, more generally, do we want to make threads individually addressable in terms of message communication targets and sources? We have not settled on how to do that yet. So according to the MPI standard, The only unit that we care about is the process. We argued about should we in Open MPI do something a little beyond that and make the threads be individually bindable and so on. We kind of fell down on the side of no, because we can do all this stuff at startup for you. But then if you want to do something more than that, you should probably just use HWLoc itself. Just link in the HWLoc library, make their function calls, and you can bind to things how you want to do. That being said, this falls in that area of we don't know what you want. So if there are common things that you find that you want to do with, like, I always want to bind my threads in a different way, tell us. Let us know. And that's something we can look at. Yes, sir.
So how is the new performance different from the profiling?
Great question. So the question is, how is the new MPIT performance variable interface different from the old profiling interface? They're different and the same, shall we say. The old profiling interface is still there. So just to be totally clear on that, all your old favorite tools will still work the way that they used to work. This is a new additional way to grab information from underneath that was never exposed before. So I can expose to you information about my NIC, right, that you can't get from just intercepting MPI send, right? With MPI send, I can count how many times you called MPI send. I can even say, average buffer size and things like that. But I can't say how many retransmissions went out the NIC, right? So I can expose really deep, dark, nasty information up that you did not have visibility to before. And even other things like, well, it's early days. We haven't decided what we're going to expose yet. but stuff that you can't just get from intercepting MPI calls. There's a lot of state underneath. Could be hardware oriented, could be just MPI layer oriented, right? That was what I was trying to come up with a second ago, an example like what could I put in the MPI layer that you couldn't get from PMPI, and I don't have an immediate example off the top of my head. But there's still a lot of state in the MPI layer that's independent of the hardware that might be useful to expose to you. Honestly, we went for the hardware layer first because that's where the most uniqueness is, and that's where we wanted to kick the tires. It'll slowly spread out from there. Now, the thing that's a little bit of a bummer is that this MPIT interface, this is, we've done it this way in Open MPI. We have these set of names and performance variables and control variables. MPitch and all the others, totally different names, variables, and meanings for their names. The reason for that is basically we argued about this a lot. We decided that we could never agree on the information that we're going to expose and what they mean and so on. So let's just provide a general way for you to discover what is there and get to it that way and so on. So it is a little bit of a bummer that we're not going to be uniform across the MPI implementation. The API is the same, but the names and the meanings of them are not the same. Eric. They might be different. So the canonical example of this is everybody's like, well, what about the eager limit? I just want to know what the eager limit is. OpenMPI and MPitch have incredibly different definitions of what an eager limit is. And even within the transports, OpenMPI has a different definition of exactly what an eager limit is. So it's complicated, and it's not appropriate to standardize that. So we said, let's not standardize, let's just give you a way to discover it. No, we don't have any kind of gentleman's agreement on that, so to speak. We do, so the best we give is that, and I think MPitch copied us, I'm not 100% sure of this. In OpenMPI's MPI.h, there's a pound define for OpenMPI, right? So OpenMPI will be defined to 1 if you're in OpenMPI. And then all of our, I'm sorry, just flashed on the screen. I need to repeat the question. I'm sorry, I forgot. The question was, is there any differentiation in the names between MPitch and OpenMPI and the others? Like, for example, if I ask for eager limit, do I know that that's the OpenMPI eager limit or the MPitch eager limit or the Cray MPI eager limit or whatever? The answer is no. Yeah, we did agreed to just not standardize on the names at all, to mean that yes, you could have the same name in multiple MPI implementations. I think that would be pretty unusual. Open MPI's names are very well structured and formed. We've got that prefix rule like BTL, TCP, buffer size, blah blah blah, and I can't imagine those would exist in MPitch. But you know, never say never. I'm sure there's going to be a collision somewhere.
So I was curious when you're doing your map of all those resources. Maybe you covered this. I apologize, but not all those resources may be available, right? They may be taken by other processes, for example. So when you're doing your ordering,
yes.
I mean, does it just skip over resources that?
Yeah, we're basically assuming that somebody, usually the resource manager, tells us which ones are allowed to have.
Okay.
Right. So like if you're on, say you're on some gigantic SMP where there's 100 ports and Slurm is giving some of them to somebody else, only you have these ones. Slurm's going to do like a processor set, a C set.
I see.
And we will read that and say, oh, we can only have cores 37 through 18.
Okay.
Those numbers didn't make sense.
But I know what you mean. Yeah, some resource.
So we gather all that stuff up first. We send all that stuff back to MPI run, which then makes the map.
Okay.
And things like that. So we pay a price for the collection,
right?
But it's accurate and repeatable. That
okay, cool. I was wondering how that happened. Thank you.
Sure. Mainline kernel checkpoint restart. If I type, will he see it?
Yeah.
We can hear you. Are you referring to CRIU? Yeah. Code by OPAVL. Oh, yes. So it is CRIU. So the state of the world with Open MPI checkpoint restart is that actually with Paul and Eric, who are here in the room, we did a bunch of checkpoint restart work a long time ago, and it actually worked very well. It has unfortunately bit rotted. Oh, now everybody in the room is listening. So, okay. The state of the checkpoint restart card in OpenMPI is that it has bit rotted. On the development trunk, we did a major refactoring of our runtime support, and the checkpoint restart stuff didn't keep up with it. So checkpoint restart is currently broken in OpenMPI, so we kind of regressed on that feature. That being said, it is actually very important to Intel. And so they have publicly announced that within the next couple of months, they're going to fix it. So fix all the checkpoint restart support in OpenMPI so that it is working again. I don't know whether that's going to make the 1.7 series or whether it's going to be 1.9. I'm not sure. But the point of all that is that underneath what is the underlying checkpointing system, whether it's the Berkeley Lab checkpoint restart, BLCR, or one of a couple others to include CRIU, the code by the Parallels guys, Pavel, I can't pronounce his last name. That's just a plugin for us. So we have a plugin for BLCR. We have a plugin for a couple others. It just came up recently about the CRIU stuff. And I literally just sent some emails to the CRIU list yesterday. It was earlier this week because they were talking about OpenMPI and checkpoint restart. And so we were having a discussion of what they provide versus what OpenMPI's requirements are. It was actually, it looks very promising that somebody could write a plugin for CRIU very easily if they so desired. No one's doing it right now, and like I said, everything is broken at the moment anyway, but Intel will hopefully fix that over the next 2-3 months, and then we'll actually be back in business. So I forgot to say that in the section there, Paul, and somebody online asked me. Sure. So the question is, what does the out-of-band communication do in OpenMPI? Well, it basically does out-of-band communication. It's used for bootstrapping. So when MPI run starts up your process, we send a bunch of control messages around saying, here's the name of the executable to start, here's the directory, here's the environment, here's the map, here's the binding, do this binding, do that ordering, stuff like that. So there's the whole launch message sequence that's done. And then similarly at the end, there's cleanup message, or if you hit Control C, right, we basically forward that out to all the little helper daemons, and they do Control C to all your things. So all the control stuff around that. Standard out and standard error and standard in forwarding is all done via our out-of-band mechanism because it gets really complicated, basically. There's no reliable standard out forwarding from all these different launch mechanisms, whether it's via a job scheduler or even SSH, particularly if SSH is done in a tree-based fashion or something like that. So we just intercept all those file descriptors of the processes that we launch, slurp in the standard out, standard error, and then out of band send it back up to MPI run, and then send it out MPI run standard out standard error. So that you can do MPI run blah 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 and a Waka symbol and a thing and a file name, and it all goes into that file name, right? If we didn't do it that way, then the standard out and standard error would end up elsewhere, right? You wouldn't get it nicely redirected to the next thing, the next pipe. Other stuff, there's a small number of other places that we're actually trying to stamp out. So in the InfiniBand BTL, for example, we do lazy connections. So we don't make a queue pair to a peer until you do the first send or receive, send to that peer. And the way that you make RC queue pairs is you have to make your end of it, and you get some unique information, and then send it to the other side. Right, so it's not like a TCP socket, for example, that you open an endpoint and you have a port, and you can send that port to everybody. You get lots of incoming people into that one port, which under the covers does other things, but you have one endpoint you can tell everybody about. In InfiniBand, you get a unique endpoint every time you open a new one, and you have to send that to the other side. So we do that via the out of band as well. Right, so and that's very much because we do this lazy wire up to conserve resources. So those are the, I think those are the big things that we use the OLB for. If you're using InfiniBand, usually you'll see big bursts of it in the beginning and then a smaller burst of it at the end, because in most applications, you're going to communicate with who you communicate with right away. And then after we set up that queue pair, there's no need for RML or OOB anymore. So yes, if they're doing standard out, yes. And that will slow down your process, particularly if they're doing truckloads of standard out. Bad idea. Tell them not to. Smack them on the nose. Tell them not to. In Open MPI socket-based communications, both out of band and in MPI, if you're using gigabit Ethernet or something like that, sometimes you can get port scanners that come in and basically confuse Open MPI, and you could end up even crashing the program. We have talked about before, because I have run into that same problem at Cisco. So not even in the out of band, but in the TCP BTL itself. We have talked about putting some kind of authentication is a too strong of a term, but like a special token that upon connection, I should get this token, and then I know it's Open MPI on the other side. And then I'm good. Otherwise, like, oh, it's probably a port scanner, I should just close it and move on. We've never had enough people ask for it because it's a little complicated to do. But if you could send something to the, say, the users list and describe what you just said and say if there's a way that we could be, a little more hard to port scanners and stuff, that would be useful. So the question is, how difficult is it to change BTL in the middle of a run, for example, because of migration? I will say that definitely worked at one point in Open MPI. So Josh Hersey did a lot of work of that. He's a professor at the University of Wisconsin-La Crosse right now. But he previously had exactly that feature working, that you were running on one set of networks and you did a checkpoint and you killed it. And then you came up in a different set of machines and you used a different set of networks. So like even I was using InfiniBand, now I'm using TCP. That was very definitely working because basically when you restart, we're kind of replaying MPI and NIC, kind of. And so it's pretty much that we can just say, let's rediscover the networks, and I'm reassigning endpoint addresses and stuff at that point. So it doesn't matter if all the networks are now different. I'm rediscovering everything. So hypothetically, my boss asked me about this last week. Hypothetically, once we get the infrastructure fixed for all the checkpoint restart stuff, that feature should still be working. The point was made that we have to synchronize to do that. And yes, OpenMPI's approach to checkpointing is synchronous. So even if you just migrate one process, everybody will pause and learn where that guy went and so on. The University of Tennessee did a whole pile of work in uncoordinated checkpointing. I don't know how featureful it was. They do have, what's it called? They have a website for this, which George Basilica is going to kill me because I don't remember the name of it. Paul, do you remember what it is offhand? Shoot. I think it's faulttolerance.org. I think it's something as simple as that. But they basically kind of forked Open MPI and did a whole pile of uncoordinated And they did some neat stuff. It's worth going to look at. I can't speak to it very well because I would just get it wrong. But I don't know if they supported that kind of thing, like, oh, you were running on InfiniBand, now you're running on TCP in an uncoordinated fashion. For us, shared memory is just another network, right? So this same thing, like if you checkpointed 2 processes and one ended up over here and now another one is over here and they can't use shared memory anymore, to us, that's exactly the same as I was using InfiniBand and now I'm not. The question is, did we optimize some of this for process migration? Now you get into the stuff that Josh did that I really can't answer very well. So I know he did do a lot of work to make it work fairly robustly. And the coordination that's done is not as heavyweight as it sounds. I mean, what we basically do is drain the networks, right? Because we can't checkpoint something that's in flight. And for certain types of networks like InfiniBand, we actually shut down all the queue pairs, unregister all the memory. So that part kind of sucks because you can't checkpoint the hardware, right? The whole point of these super high-speed networks is that you're offloading out of it's not in the state is not in the operating system. The state is in the hardware. So you basically have to shut down the hardware so that you can have a checkpointable process, right? So that part is kind of, you're right, that part's kind of heavyweight. But the coordination to drain the networks and then the coordination to find out where everybody is again is not that terrible. And at scale, yeah, I'm sure it is kind of terrible. But for medium-sized jobs, it's no worse than writing out the core files, right? It's significantly better, actually. Paul. Okay, thank you very much. Paul just confirmed it is fault-tolerance.org. That's the university site, or University of Tennessee site, where they did a bunch of nifty stuff for fault-tolerant things.